Tonight's presentation is selecting, preserving, and preparing your engine. And our presenter is Mike Bush. Mike is president of Savvy Aviation Incorporated and author for numerous aviation pubs, and holds CFI certificate, AMP certificate with IA authorization, maintenance technician of the year with the FAA in 2008. Of course, a monthly contributor to our normal EAA webinar series, runs the first Wednesday of every month. Mike's been doing it as long as we've been doing webinars, over 10 years. So really happy to have Mike and his expertise on engines on tonight to be talking to home builders. Mike, I'm going to turn control of the presentation over to you.
Okay, Tim. Evening, everybody. Let me bring my screen up here. Glad to be hanging out with 400 or so of my best friends here. So as Tim said, we're gonna be talking about engines tonight, and I want to talk about some of the challenges that are particular to home builders. Got a lot of material here, so I'm going to go through it pretty quickly because I'm hoping to leave some time at the end for some Q&A. But you know, home builders have some special challenges when it comes to engines. One of the problems is that the engine often arrives long before it's ready to be installed and run in the airplane, and that creates some issues. And then the other really unique thing is once the airplane is ready to fly, the procedures that you would want to follow for first flight tend to conflict with the procedures that you would want for optimum break-in. So we'll talk about how we can try to reconcile those things. So first of all, selecting engine. Piston engines just hate to sit unflown. When they do, they tend to corrode. Protective oil film on critical parts tends to strip off over time, exposing those parts to corrosion pitting. Cam and lifters are particularly vulnerable, also cylinder barrels. And then the corrosion pitting can be almost microscopic, but then once the engine is started, particularly if it's not pre-lubricated when it's started, that pitting will get mechanically enlarged, and things like cam lobes and lifter faces and so on will start to come apart. And this is worst. I mean, it's always bad for engines to sit unflown, but it's worst with a freshly built engine, one that just came from the factory or just came from an overhaul shop, because freshly built engines are exquisitely vulnerable to corrosion until they've flown long enough to build up a protective layer of oil and varnish. The cylinder walls will build up a protective coat of varnish and will be more corrosion resistant after they've run for a little while. But when they're brand new and freshly honed, they're extremely vulnerable to corrosion, and you simply can't let them sit. I managed to find this photograph. Ram Aircraft in Waco, Texas, did this photograph of a Continental engine that had sat without any protective oil film on it for 7 days, presumably in Waco, Texas. I'm not exactly sure, but that's where I am guessing this happened. And you can see the amount of corrosion damage that occurred to that engine in just 7 days without any protective oil film on the parts. Here's some other photographs of engines that sustained damage after sitting for a long time unflown. So in a perfect world, we would like to try not to take delivery of the engine until you're ready to fly. Unfortunately, in the real world, that doesn't happen very often. First of all, right now, lead times on engines are absolutely ridiculous. And that's true whether you're trying to get one from the factory or whether you're trying to get one from an overhaul shop. There are huge supply chain problems. There are huge problems with labor shortages, kind of COVID-induced. People aren't wanting to go back to work, and so we're seeing lead times of 6 to 9 months on engines. This is a terrible time to need an engine, and with lead times this long, of course, if you're building an airplane, you're going to need to order the engine well before you need it. And then, of course, builders always underestimate how soon they're going to be ready for the engine. So if you order the engine when you think you need it and you add all this lead time that it's going to take to get it, chances are pretty good that it's going to come before you're ready for it. And of course, nobody wants to finish building an aircraft and then have no engine to put on it. That's very frustrating. So in the real world, it turns out that engines typically do arrive before you're ready for them. And if that happens, which it generally does, you're going to have to take some heroic measures to protect the engine against damage while it's sitting there waiting for you to finish building the airplane to the point where you can hang the engine and start running it. So let's talk a little bit about preserving engines while they're waiting. And there are really two things that you can do. One is pickling the engine, and the other is using an engine dehumidifier. Pickling the engine is pretty easy. Both Continental and Lycoming have service bulletins that describe the procedure. Actually, Continental moved it from a service bulletin to their standard practice maintenance manual, M0. Lycoming, it's still in a service letter. Tannis makes a nice little pickle kit, I think they call it, that you can buy on Aircraft Spruce that has all the stuff you need to pickle an engine. Or if you want to build your own pickle kit, here's pretty much the stuff you're going to need. You're going to need some sort of an anti-corrosive aerosol spray that you can spray into the cylinders through the spark plug holes. You're going to need some desiccant plugs that you put in the cylinders in place of the normal spark plugs that will absorb any moisture and keep the combustion chambers moisture free. You're going to need some anti-rust preservative oil. Phillips makes something called anti-rust aviation oil, 20W50. Aeroshell makes a preservative aviation oil with a very unappealing name, Fluid 2F. I don't know where the heck that came from. But in any case, either of those are good preservative oils. They're thick and they're gooey and they stick like glue, and they've got all sorts of additives to inhibit corrosion. It's not an oil you'd normally want to operate the engine on, although they are approved, I think, for up to 25 hours of operation with that oil in them. But normally we don't run them for very long with that oil in them, usually just long enough to distribute the oil around the engine. You're going to need some bags of desiccant that you'll stick into the induction system and the exhaust system, and then you'll seal it up with duct tape. So you're going to need some duct tape. I think all of this stuff you can buy at Aircraft Spruce or whatever. But that's basically what's involved. Normally, when we pickle an engine that's on an airplane that's about to go inactive for a while, we'll put the anti-rust oil in and run the engine to get it all distributed around. If you have an engine on a pallet that isn't in an airplane, you're not going to be able to run the engine. So what you're probably going to want to do is put the anti-rust oil in and then flip the engine upside down and back right side up and try to get that oil all over everything that you can. Not quite as good as running it, but you do what you have to do. So in addition to pickling it, you can use an engine dehydrator. And an engine dehydrator is just a simple little device that has a little air pump that blows a small volume of air through something that dehumidifies the air, and then the dehumidified air is then run through a tube, typically into the engine breather or the oil fill or something, so that the idea is that the crankcase is slightly pressurized with very low humidity air, which basically prevents any humidity from getting in the engine, keeps everything dry. There are a couple of kinds of dehydrators you can buy. The Engine Saver, I think, is one that you can buy at Aircraft Spruce that basically has a little pump. I think it might be a adapted aquarium pump or something. It doesn't take a very big pump to do this. And then a jar that is filled with desiccant crystals, and the pump pumps air through the jar. The desiccant dries it out, and then the dried air then gets plumbed into the engine. Then there's another one called a Black Max. I think you have to buy that directly from the manufacturer. It's a little bit more expensive, but instead of using desiccant crystals, it basically uses a refrigerant. It works kind of like a room dehumidifier, and the advantage of it is that the desiccant, never has to be replaced. If you use a desiccant type thing, you have to periodically either put new desiccant crystals in or take the old ones out and put them in a microwave or something to dry them back out again. The refrigerant kind just runs and doesn't have any consumables other than electricity. But either one of those will keep the engine bone dry inside and will go a long way to inhibiting any corrosion, particularly in the bottom end of the engine. The little desiccant plugs do a pretty good job of protecting the combustion chambers, and the dehumidifier keeps moisture out of the bottom end of the engine. So if you pickle it and you use an engine dehydrator, then the engine can sit for a year or two if necessary, and won't corrode inside. Okay, so this engine has been pickled and dehydrated, and it's sitting around until you're ready to use it, and then you get ready to use it. How do you prepare the engine for starting to get used? And the key to preparing the engine is pre-lubrication, because we don't want to start the engine dry. And so there are a number of tricks you can use to make sure that the engine is as pre-lubricated as possible. And our engines were not really designed to make it particularly easy to do, but here's some procedures you can use to pre-lubricate the engine and try to minimize basically what we're trying to do is minimize the amount of damage that happens during the first couple of minutes after you start the engine until splash oil has had a chance to put a good thick oil film over everything. So we want to remove the spark plugs, or if the engine was pickled, the desiccant plugs. Rotate the prop to bring each piston to bottom dead center, and then fog the combustion chamber of each cylinder with some kind of a penetrating lubricant. And it's best to fog it in through both the top and the bottom spark plug holes to get the best coverage. You can use aerosol, but I like to use this little $17 pump sprayer that you can buy from Amazon. That is basically a pressure pot. You put whatever your favorite lubricant in there, Aerocroil or LPS2 or Corrosion-X or something, and then you pump it up with that little pump on the top of it, and that pressurizes the jar and it will spray the oil out as a very fine mist that you can direct in through spark plug holes. And after you've pre-lubricated all the cylinders, you want to do what you can to pre-lubricate the bottom end, and at least to try to get some lubricant on the cam and lifters and so on, which are the high stress points when you first start the engine in the bottom end. So you can use the same kind of a pressure sprayer to fog oil into the crankcase through the breather and the oil filler. The top two photos show the breather and the oil filler on a Lycoming, and the bottom shows the breather and oil filler on a Sandcast style Continental engine. The Permold engines have a breather that's combined with the oil filler, so you just have one place to fog it in on a Permold style Continental. But basically, we're just trying to get as much of this oil mist into the engine so that so that when we first start the engine, things aren't dry. Now, with the spark plugs still removed and the mixture at idle cut off, because we don't want to start the engine yet, you want to crank the engine with the starter in 30-second bursts until you start to see oil pressure register on the gauge, because we want to get oil into all the oil galleries, and we want to get oil extruding into the main bearings and rod bearings and so on before we start the engine. And we need to limit the starter operation about 30 seconds so it doesn't overheat. After you crank it for 30 seconds, if you don't have oil pressure yet, you probably won't in the first 30 seconds. You want to let the starter cool off for a couple minutes and then crank it again for 30 seconds, and just keep doing that until the oil pressure gauge comes off the peg, so that you know you're establishing oil pressure in the engine. And once you've done that, you've pre-lubricated things as much as it's possible to do, so you can reinstall the spark plugs, and you're ready for the first start. So let's talk about the first start. You want to do the first start with caution. You want to avoid over priming the engine, because that is going to wash all that pre-lube off the cylinder walls. So use minimum priming to avoid flooding the engine. Once the engine fires, resist the urge to rev it up. Let it run at minimum RPM. For most engines, that's around 600 RPM for a minute or two, until the engine is reasonably well splash lubricated, and then you can slowly throttle up to higher RPM, but do it slowly and cautiously. We want to make sure that everything gets lubricated before we bring the engine up to high RPM. After no more than about 5 minutes, because for reasons I'm going to get into, we want to minimize low power operation on the ground. So after no more than 5 minutes, shut the engine down, remove the cowling, inspect everything for leaks. We don't want to spend a lot of time idling the engine or running it at low power on the ground, because that risks glazing these freshly honed cylinders. And that sort of brings us to the first few hours where we're dealing with break-in and first flight and so on. And as I mentioned, first flight procedures tend to conflict with optimum break-in procedures, because first flight requires caution. This is a brand new airplane, and we need to be really cautious about it. And yet break-in requires running the engine hard. And if we don't run the engine hard, we risk glazing the cylinders and not having a good break-in, and we might wind up having to pull all the cylinders off and rehone them, which we really don't want to do. So it's a difficult trade-off. There are no easy answers. I'll talk a little bit about it, but you have to do whatever keeps you in your comfort zone. The engine wants one thing and your fanny wants another thing, and you have to try to find the right trade-off between them. But let's talk a little about cylinder break-in. There's a lot of stuff written on this subject. Continental and Lycoming have service bulletins on it. The cylinder manufacturers, PMA cylinder manufacturers, have their own ideas. Major overhaul shops have written their own instructions for break-in. Even the Shell Oil Company has something that they wrote on how to break in an engine. And there are some common threads if you read all of this material, but there's also quite a bit of disagreement about what power settings to use, what kind of oil to use, how soon to change out the break-in oil, how long the break-in should take. It can get pretty confusing. So just kind of going back to basics, let's talk about what we're trying to accomplish when we're breaking in a new engine. This is what a new cylinder looks like. This happens to be a Lycoming cylinder, but Continental cylinders are pretty similar, and it's got a steel barrel that's mated to an aluminum alloy head, and then there's an aluminum alloy piston with chrome plated steel rings that's running up and down inside that barrel. Most of our engines have 2 compression rings, and followed by an oil control ring. And some engines have a 4th ring that's down below the piston pin called a scraper ring. And some engines don't have that 4th ring. But anyway, as the piston reciprocates up and down in the barrel, the compression rings are supposed to hydroplane on a film of oil that's on the cylinder wall, so that the compression rings don't actually touch the cylinder wall, but they ride on this oil film. If they touch the cylinder wall, and then there's going to be metal-to-metal contact, there'll be a lot of wear, there'll be vertical scoring on the cylinder walls. And it's the oil film on the cylinder walls that protects against that. And the purpose of the oil control ring is to apply and keep replenishing that oil film, so that the rings can hydroplane on a film of oil. Now, when the cylinder barrel is initially machined at the factory, it comes out of the CNC machine with a mirror smooth finish. But a mirror smooth finish isn't going to work very well, because you can't coat a mirror smooth steel surface with a film of oil. If you try to do it, the oil beads up in little droplets, and instead of spreading out as a nice even film, that was what we want. Engineers say that this mirror smooth surface is not oil wettable. So we have to make it oil wettable, and the way they do that is they hone this mirror smooth surface with with some 220 grit stones to create a crosshatch pattern of tiny scratches. Those scratches are sometimes called a micro finish, because they're not very deep. They're only about 30 micro inches deep, which is not very much, but that's all it takes to turn that mirror smooth finish into one that's oil wettable, where an oil film can adhere to the surface and provide the hydrodynamic lubrication that we need to avoid excessive wear as the piston reciprocates up and down inside that cylinder barrel. So when the cylinder is honed like this, if you could look at a cross section with a microscope, you'd see there's a whole bunch of peaks and valleys. And the valleys are the things that allow the oil to get a foothold and to cling to the surface and not bead up. So we want the valleys, but the peaks are kind of problematic, because they increase friction, cause the barrels to run hot. And so the whole purpose of break-in is to smooth off those peaks and leave the valleys. And it kind of would be nice if this was done at the factory, and to some extent it is. If you get a factory engine, some cylinders use a multi-step honing process where after the 220 grit stone is used to create the crosshatch pattern, a finer abrasive is used to try to knock the tops off of those peaks. And all factory new and rebuilt engines and some overhauls are run in a test cell, which at least starts the break-in process. I say some overhauls because some engine shops have a test stand that they run their engines on, and many overhaul shops don't. And the first time the engine gets run is when the customer receives it. So it varies from overhaul shop to overhaul shop. But the factories, both Lycoming and Continental, they all run the engine in the factory, but not for very long. They run it for about an hour, and only a small part of that hour is at high power where the break-in takes place. So the break-in may get started a little bit during the test cell run, but you have to finish it off yourself. And the worst case is cylinders that are replaced in the field because they never get any run in until you do it. So in all cases, the final break-in is left to the pilot who flies the first post-install flights. So let's talk about what we're trying to do. During normal engine operation, our goal is to lubricate the cylinder barrel with an oil film that's sufficiently strong and thick to prevent most metal-metal contact between the rings and the barrel wall. But during break-in, our goal is just the opposite. We need to breach that oil film and cause sufficient metal-to-metal contact to grind off those sharp peaks of the crosshatch. So to do that, we need to run the engine really hard because it's the combustion chamber pressure, the peak combustion chamber pressure, that is actually what pushes those compression rings against the cylinder wall. The compression rings are semi-trapezoidal rings, and they're designed so that gas pressure pushes them against the cylinder wall. And so unless you're running fairly high power, we don't get a lot of force pushing that piston ring against the cylinder wall, and we won't breach the oil film, and we won't be able to do what we're trying to do in the break-in process. It's also important that the oil film not be so strong that it can't be breached. So we have to make sure we choose the right break-in oil and the right additives and so on. And traditionally, break-in is done with really simple, straight mineral oil that is just pretty much dead dinosaurs with no synthetics, no ashless dispersants, no anti-wear or anti-scuff additives or other friction modifiers, no viscosity index improvers that provide for multi-viscosity. In recent years, some manufacturers and overhaul shops have been moving away from recommending straight mineral oil and are using some more sophisticated oils for break-in. But what we definitely don't want is we don't want anything with synthetics in it, because synthetics have higher film strength than petroleum-based oils, which is normally good, but it's not good for break-in. So we want to avoid anything with synthetics in it. We also want to avoid using any anti-wear or any scuff additives, because scuffing is what we're trying to achieve during break-in. So the time to start using friction modifiers is after the first few hours of operation, after we finished breaking in the engine. I have not seen any evidence that ashless dispersant oil is any less effective for break-in. The ashless dispersant its purpose is to keep the engine cleaner by suspending particulate matter rather than letting it settle out as sludge. And so personally, I prefer using AD oil for break-in rather than straight mineral oil that does not have ashless dispersants. And I've had good success doing that. There's a little controversy over whether single grade oil or multi-vis oil is better for break-in. Traditionally, single grade oil has been used, but in recent years, more and more people have been recommending using a multi-vis oil, and I've used both, and I've been successful with both. So I don't think there's really a compelling argument that single weight is better than multi-vis for break-in. So again, the things we don't want to use for break-in, we don't want to use anything like Shell 15W50, which is a semi-synthetic 50% dead dinosaurs and 50% PAO, synthetic base stock. We don't want to use something like W100 plus, because the plus part is anti-scuff additives, which we don't really want when we're doing the break-in. We don't want aftermarket additives like CamGuard, which is wonderful stuff, and I use it in my airplane, but you don't want to use it during break-in because it's got some very effective anti-scuff additives, and so it's something you want to start after the break-in is complete. And you don't want to use something like the Lycoming LW16702 snake oil, which is a triphenyl phosphate. It's another anti-scuff additive, and so we don't want to use that during break-in. And that triphenyl phosphate is also blended in, pre-blended into W100 Plus and 15W50 and Phillips Victory oil. Several oils have that stuff pre-blended in, so we don't want to use those for break-in. We want to run the engine really hard during break-in, but the question is how hard, and this is where a lot of the different manufacturers give conflicting advice. Some say, run a combination between 75% power and 65% power. In my view, when you think about what we're trying to accomplish, we'd like to run the engine at 100% power if we could. What we don't, for an hour or two, because the more power we use, the faster the break-in is going to take place, and the more effective it's going to be. But we need to be careful not to overheat and damage these new cylinders. And new cylinders will naturally run hotter than normal because those peaks cause excess friction and so on. So, in fact, you can pretty much tell when the break-in is complete because you'll see the cylinder head temperatures come down, assuming that you've got them instrumented. So by far the best way to accomplish this is to have an engine monitor installed where you can watch the CHTs of each cylinder, and then run the engine as hard as you possibly can without allowing the CHTs to get excessive. And so for break-in, I recommend limiting Continental cylinders to 420 degrees cylinder head temperature and Lycoming cylinders to 440. And that's a little bit hotter than I would normally recommend running them, but you expect the new cylinders to be hotter until the break-in is complete. If you run the engine really, really hard, limited only by these cylinder head temperatures, and do it for an hour or two, you'll start to see the cylinder head temperatures come down, and that will indicate that break-in is largely complete. It's important to run the engine hard right from the outset with minimum ground running at low power. And the reason for that is that if you run a freshly honed cylinder at low power for any longer than necessary, it can cause a condition known as glazing. Because when you run the engine at low power, the seal between the compression rings and the cylinder wall is not very good because there's not much pressure forcing them together. And so you get hot blow-by that gets past the compression rings and starts to coke up the oil that is on the cylinder walls down below the compression rings. Now, normally that's actually a good thing. It's that carbonized oil, that's sort of a varnish layer that protects the cylinder against corrosion. But if you let it happen before the cylinders break in, that varnish is going to stop the break-in process and deaden its tracks, and you may wind up having to pull the cylinders off and rehone them, which nobody wants to do. So, just to get this across, this obviously is not to scale. I've kind of exaggerated the dimensions here, but the left pane here is trying to show what a freshly honed cylinder looks like with all those sharp peaks. The middle one is what we're trying for, which is to round off those sharp peaks, but leave the valley so that the cylinder is still oil wettable. And the right picture is showing sort of symbolically what a glazed cylinder looks like, where we've allowed a bunch of varnish to form before the break-in is complete, and that varnish is going to prevent the compression ring from continuing to abrade against those peaks. So we want to avoid extensive running at low power until we've gotten the break-in complete. And that's particularly hard to do when you're dealing with a first flight of a home-built aircraft. So just briefly, the rules for break-in: we want to use the right oil without any synthetics or any scuff additives. We want to run the engine hard, as close to 100% power as we can, without letting the CHTs get ridiculous. And we want to minimize ground and low power operations for the first couple of hours until the break-in is complete. And it shouldn't take that long if it's done right. Conventional steel cylinders should break in within about 5 hours if you do everything right. And actually, I find that you can generally do it in an hour or two if you run it at nice high power. Nickel-carbide cylinders break in very, very quickly because the carbide particles act as sort of a grinding compound, and so the break-in happens more quickly with nickel-carbide cylinders. And conversely, channel chrome cylinders, the traditional chroming kind of cylinders, take longer to break in, and they never really break into the extent that a steel cylinder will. So you will always have higher oil consumption with chrome cylinders, but that is usually an acceptable trade-off, because the good thing about chrome cylinders, they wear like iron, and they're very, very hard, and they won't rust. So that the plus of chrome cylinders is that they last a long time and they don't rust, and the negative is that they will always use more oil. So, getting back to this quandary we have, how can you minimize low power operations prior to first flight without compromising safety? That's very controversial. I have a few thoughts on the subject, but there isn't really a magic bullet. You have to recognize that the two things are in conflict with one another, and you're trying to make a compromise that works for you. We certainly can try to minimize idle and taxi time. When we're running up the engine on the ground, it's better to run it up at high power than it is to run it up at lower power. Again, we don't, low power will allow blow by past the rings, which is something we want to minimize until the break-in is complete. I'm a big fan of starting out with high-speed taxi runs, down the runway, or what you can also consider to be a rejected takeoff, where you go to full power and you start down the runways if you're going to take off, but then you abort the takeoff before you get to rotation speed. But it's very controversial. Some people are adamantly opposed to doing high speed taxi runs on home-built aircraft. So you have to do what makes sense to you. And hopefully maybe there'll be some other ideas about how you deal with this particular quandary when we get to the Q&A. So I'm just about ready to get to the Q&A. I did want to mention that 20% off deal that Tim was talking about earlier applies to my 4 books, which are all on sale at the EAA bookstore. So if you were thinking about buying them, this would be a really good time to buy them from the EAA bookstore, because they're being offered at a really good price. And with that, Tim, why don't we open it up for some Q&A?
Okay, Mike, thanks. Got some questions that have already come in. Stephen was wondering what happens to the rod slash main bearing while using break-in oil?
Well, the break-in oil is an adequate lubricant, and frankly, the lubrication needs of these slow-turning aircraft engines that we fly behind are very, very modest. The biggest problems that we have with aircraft oils is not so much not being good enough lubricants. It's keeping the engines clean and keeping them from rusting, because those are the two problems that we have with aircraft engines that are kind of unique. Um, First of all, they're extremely high blow-by engines compared to, say, automobile engines. And so that has a lot to do with the fact that they're air cooled and they have very loose tolerances. And so we get a tremendous amount of filth that gets into the oil. And our aviation oils have to deal with that filth. That's what ashless dispersants are all about, for example. And the second problem is that airplane engines tend to sit around a lot. We don't fly our airplanes as often as we drive our cars, for example. At least most of us don't. This is not a problem that we have with working airplanes that live in a flight school and fly every day, for example. But with owner-flown airplanes, the airplanes spend more time on the ground than they spend flying, for sure. And when they sit around, they are vulnerable to corrosion. So the big things we need from our aircraft oils are good anti-corrosion protection and the ability to handle filth and to not let it precipitate out as sludge. And that's also why we have to change the oil quite frequently in aircraft engines, because they're pretty filthy compared, say, with car engines. So there's really not an issue lubrication-wise with break-in oil. Even simple oil is good enough from a lubrication standpoint, but it's not. It doesn't have anti-corrosion additives. It doesn't have the ashless dispersants and so on. So we don't want to use that kind of oil for very long. But it's fine to use it, for 5 or 10 hours, even 25 hours if necessary. During the break-in process.
Let's see. Randolph says, do you recommend any kind of inspection if the engine has been sitting during the building process?
If it was properly preserved, you shouldn't really need an inspection. If it wasn't properly preserved, then I certainly would recommend sticking a bore scope in the cylinders and looking to see whether there's any rust damage in there. It's harder to inspect like the cam and lifters. Most Lycomings, if you have a flexible bore scope, you can visualize at least a couple of cam lobes. It kind of depends on the particular engine. And in Sandcast Continentals, you can also stick a bore scope through the oil filler and a flexible bore scope and work it around the crankshaft and see a couple of cam lobes. But if the engine was new or freshly overhauled and was properly preserved, I wouldn't really go to any great lengths to do any inspection. The biggest thing we want to do is inspect that the installation was right by, after initial running, make sure there aren't any leaks or anything chafing and so on.
Robert is wondering, Rotax makes many engines used in experimental aircraft and have reportedly specially lined cylinders. How does that and any other differences potentially change the recommendations here? So how about Rotax?
I don't think the recommendations are particularly different, except that, of course, in Rotax engines, we really can't look at cylinder head temperature. We're kind of looking at coolant temperature because the heads are liquid cooled. You know, as best I can tell, the Rotax engines break in very easily. They do they do very well. I'm a pretty big fan of the Rotax 900 series, but I don't think there's anything special other than the fact that we don't really have cylinder head temperature to look at. So we probably can't actually see the individual cylinders breaking in by seeing their cylinder head temperatures come down with the Rotax. They're just instrumented differently.
Sean is wondering, during the break-in period, how much leaning should we do of the mixture, if any?
Well, you know, we're trying to run the engine very hard, and we without over temping the cylinders. So we want to use every trick in the book we can to keep things cool during that first couple of hours. And so it's usual to just run a very, very rich mixture. Operating at lean a peak would be counterproductive because that's going to reduce the peak pressure in the cylinders, which is normally a good thing. And that's how I always run my airplane, but it's not the way we want to do it during break-in. It's more like trying to run takeoff power, or as close to takeoff power as you can. Yeah, you know, that kind of brings up another issue that comes up a lot, and there's no really good answer to it. But because we want to run these engines as hard as we possibly can during break-in, if you're based up in Denver, Colorado, or Missoula, Montana, or something up at high elevation, and it's a normally aspirated engine, you know, you're not going to be able to get more than, you know, maybe 70% power. And that's not an ideal situation for breaking in an engine. It is what it is. But if you have a choice of where you're going to break in an engine and it's a normally aspirated engine, it's best not to do it up at a high altitude airport, because you're just not going to be able to get as much power as you would like during those critical first couple hours. If it's a turbocharged engine, it doesn't matter, because the turbocharged engine always thinks it's at sea level regardless of where it is.
Ron comments, great information here. Each engine manufacturer typically has their own recommendations for break-in. Should we as an owner vary from these recommendations? And if one does, or how is or should that be documented if they vary from it?
That's an interesting question. You know, frankly, the engine manufacturer's recommendations, I think, are less than optimal, because they have to be written with the assumption that the engine has only primitive instrumentation. And if you have primitive instrumentation and you really don't know what the cylinder head temperatures are and so on, then you can't afford to be as aggressive, because you're operating in the blind. So the recommendation that I offered was presuming that you have an engine monitor that instruments cylinder head temperatures on each of the cylinders, so you can actually see what's going on. And if you do, then you can afford to run the engine quite a bit harder, which is a better way to break it in, because you can see what you're doing and you can be confident that you're not over temping anything. As far as documenting is concerned, it'd probably be best not to document it, because if you wind up having a warranty claim and you say to the manufacturer, oh, by the way, I got a warranty problem, but I wasn't following your recommendations for break-in, that probably isn't going to be helpful. So I would probably not try to document what you were doing.
Kent is wondering, if buying a new engine, would it make sense to pay the manufacturer to run it in longer in the test cell to break it in, or maybe do a dynamometer break-in test?
Well, to the best of my knowledge, you can't do that. I don't think either Lycoming or Continental will will provide custom services like that. At least I've never heard of that happening. I mean, if you're dealing with a field overhaul shop and the shop has a test cell, then maybe you could pay them to do a longer test cell run or something like that. But if you're dealing with the manufacturers, I don't think that they're going to be able to do something special for you like that.
Brett says, should break-in oil be used on an engine that has initially been broken in and has 100 hours, but then has sat out being preserved or pickled until being installed a few years later?
Well, look, if the engine ran 100 hours, which means presumably it got through its break-in process, and you haven't changed the cylinders, then there's no reason that then you're not dealing with a break-in situation because the cylinders are already broken in. If the cylinders came off and got rehoned, then you are. And as I mentioned, kind of the worst case situation is where you do cylinder work in the field and you put a freshly honed cylinder on an engine. It hadn't been run in at all by definition, so you're starting from scratch as far as break-in is concerned. But if the engine just ran 100 hours, got pickled, and went back into service, you're not dealing with a break-in situation. The cylinders are already broken in. All the stuff we talked about in terms of preserving it and in terms of pre-lubricating it when, before first start, that all applies. But you wouldn't be dealing with a break-in situation because you're not dealing with freshly honed cylinders.
Charles was wondering, what are the clues that an engine was not well broke in? For example, suppose anti-scuff was added to the break-in oil.
Well, I mean, the main thing you look at is whether the oil consumption stabilized at a reasonable value, because normally a brand new engine is going to use a ton of oil, and during that first couple of hours until the break-in is complete. So if the cylinders got glazed and so on, the main thing you'd notice is that the oil consumption is quite high and it's not coming down. You can also look in the cylinders with a borescope and kind of see what's going on, but the main thing would be that oil consumption is higher than what you're comfortable with.
Lee was wondering, do you recommend storing a Lycoming engine inverted if possible? And how about regularly rotating an engine stand?
I think Lycoming doesn't like their engines to sit upside down for any extended length of time. If you have an engine stand, a horizontal engine stand that lets you rotate the engine, I think it would not be a bad idea to, periodically, give it a 360 in order to get a bunch of oil back on the cam and stuff, because on the Lycomings, the cam is up at the top. But I wouldn't leave it upside down. I wouldn't store it that way.
Chip is wondering, is an electric engine pre-oiling pump a good idea for a piston engine in a home build?
Well, it's an interesting question. Pre-oilers, which is basically an electric pump that you plumb into the oil system in order to be able to get oil pressure up before you actually crank the engine. It really isn't nearly as helpful as you might think. In a Lycoming engine, for example, you can pre-oil that engine till the cows come home, and you're not getting any oil on the cam or lifters, and you're really not getting any oil to speak of on the cylinders. The only thing that gets oil on those things is splash oil with the engine rotating. All the pre-oiler is going to do is it's going to pump oil through the oil galleries and into the bearings. But we don't normally have a problem with the bearings because the oil that's in the bearings are held captive, and that oil typically doesn't strip off when the engine sits. It's oil on the exposed surfaces, which are cam lifters and cylinder walls that are the problem, and the pre-oiler doesn't really help that. Now, in a Continental engine, the pre-oiler does a little bit more, because when it pressurizes the main bearings and oil starts to extrude out the main bearings and falls down into the oil sump, on its way down to the oil sump, it hits the cam. So in a Continental engine, a pre-oiler actually will pre-lubricate the cam. In a Lycoming engine, it won't, because the cam's up at top, and gravity is working against it, not for it. Now there is an STC for a Lycoming cam that has some little holes drilled into the cam lobes that allow pressurized oil to lubricate the cam. If you have one of those STC cams that have little oil holes in them, then a pre-oiler would probably help. But most Lycomings don't have a cam like that, and so it wouldn't help. There's also another STC for Lycomings called NA nozzles that involve installing oil squirts that are designed to squirt oil up onto the cam when the oil galleries are pressurized. So if you've got a Lycoming engine that's been modified that way, then the pre-oiler would probably be more helpful. But in a stock Lycoming, it's not particularly helpful.
Stephen wonders, if you bore scope and see some surface rust on the cylinder wall, is there any amount of rust that is okay?
Yeah, light surface rust is probably going to just scrape off the minute the engine is started. So you would tell a lot more if you bore scoped it after the first flight to see after the surface rust was scraped off, to see if there's corrosion pitting left underneath or not. It's pretty normal to have a little light surface rust on cylinders if they've been sitting around, and especially if the engine wasn't properly preserved. But if it's light and it's confined to the surface, it's probably not going to be a huge problem. If the corrosion is more serious and has extended a little deeper, then it could be more of a problem.
Chip wonders if you have any recommendation on prop RPM for break-in, especially for those of us based at high elevation airports such as Denver or Flagstaff with controllable pitch props.
Well, you're since the objective is to maximize peak combustion pressure, the optimum thing would be to run at the highest manifold pressure and lowest RPM that you could. But again, if you're running close to 100% power, you're kind of limited to how much you can reduce the RPM and still stay within the allowable operating envelope of the engine. If you're at Denver and you have lower manifold pressure, you could afford to bring the RPM down lower. There are good charts in the Lycoming operator's manual that will tell you what the allowable limits are. And most small Lycomings are permitted to operate between 4 and 6 inches over square, if you'll forgive that terminology. And so I think it would be better to operate the engine over square while you're breaking it in, because that maximizes combustion pressure for a given amount of power output.
Tom asks, should I periodically rotate the prop shaft on a new engine while it sits before installation?
I'm not a fan of doing that. I think it's counterproductive. Rotating the prop while an engine is sitting simply accelerates the process of the oil moving from top to bottom. It just scrapes oil off the top of the cylinders and moves it to the bottom of the cylinders. And when we see cylinders with corrosion damage, the most likely place to see it is up at the 12 o'clock position, because that's where it's going to lose its oil film the quickest. And rotating the prop is just going to kind of accelerate that process. So I don't recommend doing that. If you want to do something really good, you could periodically pull the desiccant plugs out or the spark plugs out, whatever you've got in there, and spray some aerosol oil through the spark plug holes to just replenish the oil film on the cylinder walls. But I wouldn't recommend rotating the prop. That probably does more harm than good.
Moses asks, he said that I've heard different accounts of using Marvel Mystery Oil for preservation. Any comment on the product?
I think Marvel Mystery Oil has absolutely no preservative value, and all it's going to do is slightly reduce the viscosity of the oil, which is probably not what you want. So no, I wouldn't recommend using Marvel Mystery Oil when you're preserving an engine.
Steve wonders, is completely flooding the crankcase and cylinders with oil an option for extended storage on a rebuild prior to installation?
Well, I've heard of people doing that, but I know that Lycoming and Continental both frown on that.
And let's see here. James says, well, it's a great presentation. Why not just turn the airplane into the wind, fasten the tail to a stationary object, then run it hard?
Well, you could do that. That's assuming that your brakes aren't good enough to hold the airplane. Well, most airplanes, you don't actually have to tie it to a stake in order to do a full power run up. Although I've heard of airplanes that were like that. We were talking about the other day about something called a Baron 56 TC, which was a small B-55 Baron with Duke engines on it, and apparently you could not do a full power run up with a brake set. It would just drag the wheels along the ground because it's got so much power. But most airplanes aren't like that.
Here's a good question, since it's freezing cold in Wisconsin this time of year. Actually, I think it might be, 6 degrees now. So it's actually warm right now. It's 6 degrees. So, but Bridget was wondering, what are the rules for braking in an engine in cold temps? Can it be too cold to fly and brake in?
No, but you would want to preheat just like you always would in really cold weather. And I could get into why preheating is important, but I don't have the PowerPoint slides queued up to really show you. But basically, what happens is if you don't preheat an engine and run it in really cold weather, the piston expands a lot faster than the cylinder because the piston doesn't have any cooling air on it, and the cylinder has a lot of really cold air. And you wind up getting metal to metal contact and vertical scoring, and so you really need to preheat those engines before you start them cold, and that's true whether you're breaking in an engine or whether the engine's got 1,000 hours on it. But other than that, I don't see any problem with breaking in an engine in cold weather. In fact, it's probably a really good time because the engine's going to put out more power in cold weather than it would in hot weather.
Kent was wondering, if we want to operate at peak pressure, would it make sense to operate 50 degrees rich of peak?
Well, the problem with running 50 degrees rich of peak is that is the place where cylinder head temperature is going to be highest, and during break-in we tend to be cylinder head temperature limited, so it probably is not a great place to operate at the very, very beginning of the break-in process. We're concerned about keeping the cylinders cool until they're broken in, and so typically we do that by using a bunch of excess fuel.
All right, getting close to the end here. Let's try and do one more question here from Michael. If the cam lobes were pitted in a new Lycoming engine, what will be the telltale signs in the first 40 to 60 hours of new engine operation?
Metal in the oil filter. You typically won't. You typically wouldn't be able to tell that. I mean, I've seen Lycoming engines that had cams that were so badly spalled that you could hardly tell where the toe of the lobe is, and the pilot never noticed. But the way this normally shows up is there's a bunch of ferrous metal in the oil filter.
So that brings up the question, when do you change the oil then and inspect the oil filter after a break-in? I mean, at what point do you do that?
Both Lycoming and Continental, I think, recommend changing break-in oil at 25 hours. I tend to like to get rid of it no longer than 10 hours. It's gonna have a bunch of metal in it, and I figure the quicker we can get rid of that dirty oil, the better. If you're paying attention, the break-in's going to be over in 10 hours anyway. I don't see any reason to prolong the agony.
And then you just dump in the regular oil, whatever you're going to be using for the engine.
Your regular operating oil. I might hold off on using friction modifiers like LW16702 or CamGuard or anything, maybe until 25 or 50 hours, just to make absolutely sure. But I would normally get rid of the break-in oil and go to normal operating oil after 10 hours.
Well, Mike, great presentation. Looks like we had about 500 people logged in for it, and just some really good questions, I thought. Thank you for that discussion. Take a moment and share closing thoughts with everybody.
Well, I'm just happy to have had the opportunity to participate in Home Builders Week again. When last year was the first one of these, and I was wondering whether this was a one-hit wonder COVID-19 lockdown thing, and I'm glad to see that it's turned into a, kind of, I think it's going to be regular tradition at EAA. I think it's a good thing, so I'm glad to be part of it.
Well, thank you, Mike, and so do we. Second annual, and I'm sure there's going to be a third annual. A lot of great participation and a lot of great feedback from each presentation. When we survey everybody after all the presentations, we'll definitely see what people say. If they enjoyed it, then by gosh, we need to continue doing it. And doing it during the anniversary week of EAA is a real appropriate time to do it, I think.
Yeah. Well, next year's going to be 70, right?
70 years, yeah.
Mm-hmm.
Yeah,
so
great.
Be a big deal.
Hmm.
How come I always get scheduled at the very end?
You're the cleanup batter, Mike.
I guess so.
We saved the best for last.
Okay.
What can you say?
I'll take it.
Take it as a compliment, by gosh. All right. Well, thank you so much, Mike, and everybody who tuned in. Thank you so much for joining us. And tomorrow morning, first presentation starts at 11:30 a.m. Central, and we're going to be talking about working with wood, building wood airplanes. How cool is that? All right,
Very
folks,
cool.
have a great night. Thank you.
Thanks, everybody.